Hello guys, in today's class we're gonna solve this problem. First, let's try to understand it. It talks about digits that are non-increasing. What does that mean? So let's take, for example, a 5-digit positive integer that is the following: 9, 8, 8, 6, not 6, 2, and then 6. So this number over here is increasing. But why? Well, if you take every single relationship between two consecutive digits, for example, from 9 to 8, well, this is a decrease because you're decreasing the number. Then here, you're not doing anything, if that's a relationship. From 8 to 2, you are again decreasing, and from 2 to 6, and this is an important point, you are increasing. And what does that mean? Well, we're trying to avoid these type of numbers. The numbers that have this relationship in any of its relation. Now, note, for example, that if we take an arbitrary 5-digit positive integer like 7, 6, 2, 6, 1, even though this number is increasing because you have from 2 to 6, you can rearrange the digits in a way that it is no longer increasing. For example, you can rearrange it like 7, 6, 6, 2, and 1. You can always do this because there is only, but you can always do this because you can always arrange a set in a way that it goes from the greatest to the shortest, to the smallest. Now, let's prove that there's only one way to do this. So, let's take every single digit and put it in a number line. So here, this would be a 7, here this would be a 6, here this would be a 2, and this would be a 1. Well, here 2, 6. And because there's only one way to go from 7 to 1, so only one way to go from the greatest to the smallest, then we can note that there's only one number that fulfills these requirements from any arrangement that we have of these 5 digits. You could tell me that I have 2 6s, so I could exchange them and it would still work. However, if I have 7, 6, 6, 2, 1, and then I exchange them, the number is the same. So this means that there's only one permutation of these 5 digits that fulfills these requirements. This means that what we're actually looking for is for how many 5-digit positive integers are there, so that we don't care about the order and that we can repeat. So, what we can do is take all possible numbers. Well, let's erase this as well. We could start by 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And put sort of dividers for doing a table. Let's say we have another arbitrary number. Let's say we have 5, 4, 4, 2, 1. And what we're going to do is put 1, 5, then 2, 4, because this is what we have here, 2 4s, 1, 2, and 1, 1. Now, of course you can put zeros here, but what we're doing here, if we only take this number, this table, we're saying that we have a number with 1, 5, 2 4s, 1, 2, and 1, 1. And because we know that this representation can only work for one of the numbers that we're looking for, then what we're trying to look for is how many of this combination of numbers can we have. In order to know this, what we can do is use another representation of this number. This could be a dot, this is nothing, well, 0 dots, this is 2 dots, this is 1 dot, and then nothing. And then take the dividers. These dividers over here are important because this is what tells me what is the value of each dot. Because yes, we know that there's dots, but we have to know which number are they. And what we're doing is that everything before the first divider means how many zeros are there. So this number over here tells me that I have 1 1, 1 2, 0 3s, 2 4s, 1 5, and so on. Now, what we are now trying to look for is how many representations of this, like how many ways of having 5 dots and 9 dividers can I have? And in order to do this, let's erase this. We can note that if, for example, I happen to now put this dot here, well, this would be now the representation. And this would still be a possible option, a different option, and what we did was just exchanging spaces. So we can also represent this as having 14 spaces. Well, let's... This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 13, and this is 14. And we know that we can have in these spaces either a dot or a divider. So note that what we're doing, let's erase everything, or what we have to do is to find in how many ways can I put dots and dividers, well, 5 dots and 9 dividers in these 14 spaces. And we can do this by using combinatorics. This over here means n chooses x, right? And this means in how many ways do I have, in how many ways can I choose x from n spaces? So, for example, in this case, I have 14 spaces, and I have to choose 5 dots. So what I'm saying is, in how many ways can I put 5 dots in these 14 spaces? This is also true because if I put 5 dividers in any of these spaces, the dividers will be already in, because the dividers are all the same and we do not have to calculate them. So this would be the answer. But we have to take into account that we are also taking the position in when this happens. Dot, 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 and dividers. 9 dividers. And this over here represents 5 zeros, 0, 1, 0, 2s. So this is 0, 0, 0, 0, 0. And this is not a 5-digit number. So we have to subtract 1. There are no other representation of this, because if we have a dot in the first one, if we have the same, we only have to subtract 1, because if the divider was in another place, if the divider was here, the 1 would already be, this would already be 1, 0, 0, 0, 0. And this over here works. So this would be with the result, 14, 5, 14 chooses 5. And we could of course calculate it. This would be 14 factorial over 5 factorial times 9 factorial minus 1, but I'm gonna leave that as a homework. So thank you all for listening to me, and this is it.